Usually when we talk about a blueprint, there's, this expectation of something really rigid. Like, think about looking at a schematic for a skyscraper.
Right,
Like,
yeah,
you see where the steel beams go, you see where the concrete is poured, and it's just static. It just sits there, frozen in time.
absolutely.
But then you step into the world of modern software, specifically cloud-native enterprise architecture, and suddenly that static blueprint starts breathing.
Mhm.
I mean, we are looking at a diagnostic landscape today that functions much more like a living digital organism.
Yeah, it is the absolute definition of a dynamic system. And today's source material really captures that shift perfectly.
Welcome to the deep dive.
Mm.
For you listening, our mission today is to decode a really fascinating set of schematics we've been given. It's called the Modern Java Enterprise Blueprint, specifically revision 4.2.
Mm.
And we're going to explore how modern cloud-native applications are actually built from the absolute ground up. Systems designed not just to survive the sheer chaos of the cloud, but to integrate AI seamlessly into their core.
The specs on this blueprint are just wild, honestly.
Yeah, they are.
It boasts a 98% modularity index, an SX scalability factor, and an A+ interoperability rating.
Which is huge.
Exactly. Those ratings, especially that 98% modularity, they tell us we're looking at a system designed to have its parts swapped out, upgraded, and, scaled dynamically without the whole structure collapsing.
Right.
So we want to look at not just the mechanics of these massive architectural shifts, but the why behind them.
Okay, let's unpack this, because before we can talk about deploying to the cloud and running massive AI models, we have to understand the basic machinery.
You need a foundation.
Right. The blueprint calls this first layer the core engine, and it's powered by the Cyan module, which is Jakarta EE11. Because if you're building an enterprise app with, say, hundreds of developers, how do you keep them all from writing 100 different ways to accept a simple web request?
Right, you establish a standardized foundation for your business logic. That's exactly what Jakarta EE11 does. I mean, you don't want your most brilliant engineers wasting days figuring out the mundane details of how to unpack an HTTP payload or, how to open a database connection.
Yeah, you want those baseline problems solved universally.
Exactly, so they can focus on the actual business problems.
So the blueprint splits this core engine into three distinct areas. The first is the boundary, handled by Jakarta RESTful Web Services 4.0. The docs say it transforms incoming HTTP payloads into Java objects via automatic content negotiation.
Right.
So if we picture this entire software system as a massive high-tech manufacturing plant, the boundary is the shipping and receiving dock.
That's a great way to look at it because the outside world, it communicates in HTTP. You have these JSON or XML payloads floating around the internet arriving at your server.
Right.
But your internal application speaks Java, so Jakarta REST acts as that receiving dock manager. It instantly unboxes that external raw data and just automatically translates it into Java objects.
So the internal factory can actually work with it.
Exactly. It completely removes the need for developers to write manual parsing scripts.
Okay, so the data comes through the dock, it's properly formatted, and then it hits the factory floor. The blueprint attributes this to Jakarta CDI 4.1, describing it as the central inversion of control container managing object lifecycles.
Yeah, inversion of control.
Which, if you're a developer used to manually writing code to create every single object in your program, that phrase can sound a bit backward.
Oh, it forces a massive paradigm shift. I mean, in traditional programming, if your code needs a specific tool to perform a task, you write a command to create that tool.
You do it yourself.
Right. But inversion of control means the developer is no longer micromanaging the creation and destruction of those software objects. The framework takes control.
Okay, so going back to our factory analogy, it's like an assembly line, where the factory floor itself automatically hands the right tools to the workers exactly when they need them. Like, the developer doesn't have to walk all the way to the warehouse to find a wrench. The system knows their station, knows their task, and simply injects the wrench right into their hand.
That's spot on. It manages the life cycles invisibly. It knows when that tool is required, and it knows when to put it away to free up memory.
Right.
It standardizes the internal logic so developers aren't reinventing the wheel. They're just assembling better cars.
Which brings us to the third part of this core engine, the data bridge, handled by Jakarta Persistence 3.2 and Jakarta Data 1.0. This is basically the warehouse logistics.
Mm-hmm.
The blueprint notes that it bridges object relational impedance for SQL and NoSQL. I imagine this is how the factory stores its finished goods, whether that warehouse uses a highly structured IL system like SQL or a giant flexible open floor plan like NoSQL.
Yeah, and bridging that impedance, it really just means smoothing out the historically awful translation between object-oriented code and flat database tables.
Oh, gotcha.
By having this entire core layer so rigorously standardized, you establish this rock-solid foundation.
A perfect factory is totally useless if the power grid goes down.
Exactly.
Which brings up the reality of modern deployment. We are moving from single giant servers running in a basement somewhere to distributed cloud microservices. And the reality of the cloud is that things will break.
Oh, constantly.
Networks experience latency, downstream servers crash. So how does this beautifully standardized architecture actually survive in the wild?
Well, this is where the blueprint introduces the orange layer, the cloud layer, governed by MicroProfile 7.0. If the core was the engine of the car, MicroProfile provides the telemetry dashboard and, like, the survival gear.
Right, because in a distributed cloud, a single action from a user might trigger a chain reaction across 50 different microservices scattered all over the place.
Exactly. So the blueprint lists telemetry 2.0, specifically open telemetry, as the first piece of survival gear. It tracks metrics, logs, and traces across service boundaries.
So if a customer's order gets lost somewhere between the billing microservice and the shipping microservice, open telemetry is the detective that tells you exactly where it vanished.
Yeah, because without distributed tracing, finding an error in a cloud environment is literally like finding a needle in a haystack in the dark.
Yeah, sounds miserable.
OpenTelemetry attaches a unique trace ID to a request the exact moment it enters the system, and it passes that ID along to every single microservice that touches it. So you get a perfect map.
That's incredibly useful. And then the next survival tool is Config 3.1. The blueprint shows that you can use dynamic external variables to override internal properties without recompilation.
Right.
So you don't have to shut down and rebuild the entire factory just to change the thermostat. You just turn a dial on the outside of the building.
Exactly. And you also have Health 4.0 checks acting as the pulse of the application.
The liveness, readiness, and startup checks.
Yeah, the system is continuously broadcasting its status to the cloud infrastructure saying, I'm alive, I'm ready for traffic, or, hold on, I'm still starting up.
Okay, so I want to push back on the fourth component of this survival gear, which is fault tolerance 4.1, specifically the circuit breakers.
Yeah.
Because the blueprint shows 3 states for a circuit breaker: closed, open, and half open. When it's closed, data flows smoothly. But wait, if the circuit is open, that means it's failing fast. Isn't intentionally breaking the connection a bad thing for the user? Why are we fast failing?
What's fascinating here is that it totally feels counterintuitive to intentionally block traffic.
Yeah, it really does.
But imagine a scenario where a downstream payment service starts timing out. Like, instead of taking 30 milliseconds to respond, it's suddenly taking 30 seconds.
Okay.
If the circuit stays closed and just keeps accepting traffic, every new user trying to buy something gets stuck waiting in that exact same massive traffic jam.
Oh. And the server's holding open all those connections, so it's rapidly running out of memory.
Exactly. The threads back up completely, and eventually the entire server just crashes. An open circuit acts as a protective release valve.
Ah, I see.
It detects that the payment system is struggling and instantly fails any new requests. It completely prevents cascading failure and system overload.
So it's better to just drop them quickly.
Yeah, better to give one user a swift, graceful error message or trigger a fallback option like saving the order for later than to let the entire network slowly collapse.
That makes a lot of sense. So then the half-open state is just a probe mode.
Exactly. It carefully tests if that downstream service has recovered by letting like a tiny trickle of traffic through before fully opening the floodgates again.
Brilliant. But okay, if we have dozens of these recovering, highly independent microservices chattering away with each other across a cloud network, how do they know who is allowed to talk to whom?
That's the big question.
Because trusting every request in a distributed system seems like a massive security bottleneck.
It is. Trust is incredibly difficult to scale. I mean, if every single microservice has to call a central security server to double-check a user's identity every single time it receives data,
You would just crawl.
you create a massive bottleneck. Yeah, it would slow the entire application down.
So let's trace the security context propagation in the blueprint, because it solves this so elegantly in 5 steps.
Let's do it.
Step 1, the user authenticates once. Step 2, the identity management server-like keycloak mints a signed JSON web token to JWT. Step 3, the API gateway attaches that token to the HTTP header.
Right.
And then step 4, the downstream microservice microprofile validates the RSA signature on that token without ever calling Keycloak back.
It validates it locally using a public key.
It reminds me exactly of a VIP festival wristband.
Oh, that's a perfect analogy.
Right. When you get to the festival, you show your ID at the main gate. That's your central identity server. The gate attendant verifies you and slaps a cryptographically secure VIP wristband on your arm. Now, as you walk around the festival and try to get into like the VIP comedy tent or the music tent, which are our microservices, the bouncer at each tent doesn't need to radio back to the main gate to check the master guest list.
Right. They just look at the watermark on the wristband.
Exactly.
Yeah.
The trust is totally decentralized.
And in that scenario, the microprofile validation is the bouncer checking the watermark. And then for step 5, once it's verified, the internal factory floor manager, Jakarta CDI, seamlessly injects that security context directly into the business logic, like with an @inject JSON web token command.
So the developer can just ask for the user's ID, and the system provides it instantly and securely.
Exactly. And all of this complex routing, the health checking, the security validation, it's all being overseen by the infrastructure control plane.
Which the blueprint shows as Kubernetes. It's the absolute master of this domain. It manages the ingress rules for incoming traffic, handles the config maps and secrets, and manages the stateful sets for pod identity.
Yeah, and it relies on those continuous microprofile health probes we talked about to decide if a piece of software needs to be restarted, all built on a foundation of Docker or Podman OCI images.
So Kubernetes acts as the invisible conductor of the orchestra.
Totally. I mean, it doesn't actually care about your business logic or what your code does. It cares entirely about state and health.
Yeah.
You tell Kubernetes what the desired state of the system is, and it works tirelessly to maintain that state, shifting traffic around and restarting containers as needed.
Okay, so we have the security, the telemetry, the container orchestration. But what are the developers actually writing their code in? Because the blueprint lists 5 different frameworks in the cloud-native arena.
Right?
Why wouldn't a team just pick one framework and stick with it?
Well, because developers have to make architectural trade-offs based on the specific battle they're fighting. One size definitely does not fit all.
Okay, let's break them down. The blueprint starts with plain Jakarta EE. It says it's heavily optimized for complex multi-layer systems. Then there's Spring Boot, which provides highly opinionated defaults and allows for incredibly rapid development, though it carries a moderate to heavy memory footprint.
Right, it's a bit heavier.
Then we get to the newer generation, Quarkus and Micronaut. The documentation describes them as exceptionally fast, perfectly suited for serverless microservices, and heavily utilizing Grell VM for ahead-of-time compilation. Micronaut specifically highlights zero memory overhead from this compilation. And then there's Helidon, which is a very fast, lightweight implementation for pure reactive services.
Exactly.
But wait, if Quarkus and Micronaut are exceptionally fast and perfect for serverless, why wouldn't everyone just use those? Why even bother with the moderate to heavy Spring Boot or Jakarta EE?
It's a fair question. But faster isn't universally better if it doesn't actually fit the ecosystem you're operating in.
How so?
So Java traditionally uses just-in-time compilation, which analyzes and optimizes code while the program is actively running.
Okay.
That requires a heavy Java virtual machine, which takes time to start up and consumes significant memory.
Right.
Quarkus and Micronaut, on the other hand, use ahead-of-time compilation. They do all that heavy lifting during the build process, resulting in this tiny, lightning-fast native executable.
Which sounds perfect for serverless.
It is brilliant for a serverless function that needs to wake up in a millisecond, do one task, and shut down.
But less brilliant for a massive legacy banking system.
Precisely. If you have a 20-year-old financial application with millions of lines of heavily intertwined transactional logic, you can't just shove that into a tiny ephemeral serverless function.
I see.
Ahead-of-time compilation restricts certain dynamic features that older enterprise code relies on heavily.
Got it.
And Spring Boot, well, it has a massive ecosystem of pre-built integrations. If you need to prototype rapidly and connect to a dozen obscure, older database systems, Spring Boot is unparalleled. You need those robust, heavy-duty standards to modernize massive systems safely.
Okay, that makes perfect sense. So we've chosen our framework. We have the code, the cloud resiliency, and the security. But before any of this goes live and real users touch it, how do we know it actually works?
Testing.
Right, the QA foundation, the green layer. And here's where it gets really interesting, because the blueprint contrasts the old way of testing with the modern way.
Testing is traditionally where theory crashes brutally into reality.
Seriously. In the old way, developers used mocked databases, like Mockito and in-memory H2 databases, to run their tests. The code would pass with flying colors locally on the developer's laptop and then literally explode in deployment due to SQL dialect mismatches.
Oh, happens all the time.
It's like practicing for a marathon on a treadmill in an air-conditioned room. You run 26 miles, you feel great, your watch says you passed the test.
Right.
Then you show up on race day, and the actual course is up a literal mountain in the freezing rain. You just immediately collapse.
That is exactly what it's like. It works on my machine is the oldest, most tired excuse in software engineering.
Yeah.
And in a world of complex distributed cloud systems, it's just completely unacceptable. If your test environment doesn't perfectly match your production environment, your tests are simply giving you a false sense of security.
Because the mock database might accept a date format that the actual production database will totally reject.
Exactly. So the modern way outlined here uses the test containers paradigm. It uses JUnit to spin up genuine ephemeral database containers, like a real PostgreSQL instance running in Docker, just for the test phase.
It brings the mountain to the lab.
Yes. It guarantees 100% production parity, and production parity is the only path to reliability.
Because those containers run the exact same binary code as the databases you'll use in production.
Right. You eliminate the SQL dialect mismatches entirely. If the test passes against the test container, you have cryptographic confidence it will work in the real world.
Wow. Okay, so we've built an impenetrable, perfectly routed, highly tested fortress. Now, it is time to give it a brain. The final layer of this blueprint is the violet layer, the AI tool belt.
This is where everything we've discussed converges. The entire tech industry is rushing toward AI. But bolting AI onto a fragile, poorly tested system is a disaster waiting to happen. You need that resilient core first.
So true. The blueprint categorizes the Java AI toolbelt by the specific domain of intelligence. You have DJL, the Deep Java library, handling predictive machine learning and allowing you to swap backends like PyTorch or TensorFlow natively. You have Deep Learning 4J integrating with Apache Spark for large-scale distributed training. You even have expert systems like Optiplanner and Drools for complex resource allocation. But the one dominating the conversation right now is LangChain 4J, built for generative AI, with connectors for OpenAI, Claude, and Retrieval Augmented Generation, or RAG.
Yes, LangChain 4J is huge right now.
But wait, when people think of AI, they think of Python. Why go through all this trouble to integrate AI directly into the Java enterprise stack?
This raises an important question because you're right, Python is absolutely the lingua franca of AI research and initial model training.
Yeah.
But think about the concept of data gravity. Where does the actual valuable enterprise data live?
In the databases we were just talking about.
Exactly. The billing records, the customer profiles, the highly secure transactional histories, they already live deep inside these massive Java enterprise systems.
And you definitely don't want to extract terabytes of sensitive data just to feed it to an AI.
No. Moving data is expensive, it's slow, and it's a massive security risk. By using tools like DJL and LangChain 4J natively, companies can execute AI workflows securely right where their data and their business logic already reside.
That makes so much sense.
Take Retrieval Augmented Generation, or RAG. A large language model doesn't know your company's private HR policies, right?
Right.
With RAG in Java, the enterprise system can securely fetch the exact private document the user is asking about, package it up, and hand it to the LLM to summarize all, without the sensitive data ever leaving the controlled environment.
You keep the AI inside the walls of the VIP festival.
Exactly. You don't rewrite your core applications in Python. You bring the AI to the Java data.
Okay, the blueprint brings all of this together in a final diagram, the anatomy of an AI-enhanced microservice. Let's trace a single request down the full stack.
Okay, walk me through it.
So a user asks a question via a web interface. The request hits the Kubernetes ingress controller, which routes the traffic to the correct container. Keycloak intercepts the request, validates the cryptographic signature on the JWT wristband, and grants access.
Perfect. Then the request hits the Jakarta REST boundary, which translates the HTTP payload into Java objects.
Right.
The internal CDI factory injects the necessary business services. Meanwhile, the cloud resiliency layer is watching every millisecond of this.
Yeah, the circuit breaker is monitoring for timeouts, and OpenTelemetry is recording the exact path for the dashboard.
Exactly. And then the AI integration fires.
Right. LangChain 4J executes a secure ARG query, pulling relevant context from the enterprise database, connects to an LLM, and generates an insight. The system takes that AI-generated insight and uses Jakarta data to save it safely to a PostgreSQL database.
And we know the entire flow handles the database transaction flawlessly because test containers validated the exact sequence in the deployment pipeline before it ever reached production.
It is just a beautifully orchestrated flow.
It really is. It takes the inherent unreliability of cloud networks, the massive complexity of security, data persistence, and the unpredictability of generative AI, and it wraps them all in a highly modular, testable structure.
We set out to decode this blueprint today, and it's clear that this is about so much more than writing code. I mean, we started with the basic HTTP inputs of Jakarta EE.
Yeah.
We made it bulletproof with MicroProfile and Kubernetes.
Mhm.
We tested it with real-world test containers. And finally, we injected it with generative AI using LangChain 4j.
You know, stepping back and looking at the whole picture, there is something profound happening here.
Yeah.
This blueprint proves that we can seamlessly snap together the reliability of legacy enterprise architecture with the cutting-edge capabilities of autonomous AI agents, basically like Lego bricks.
Right, so the bottleneck is no longer the technology.
No, the bottleneck is our imagination, because if we can build a digital organism this resilient, this thoroughly monitored, and this capable of understanding complex context natively, what happens next?
What do you mean?
Well, what happens when these microservices stop just passively answering our queries? What happens when an application analyzes its own open telemetry data, identifies an inefficiency, and independently uses its own embedded AI to redesign its code and redeploy itself to serve you better?
Oh, wow, and an architecture that doesn't just survive the cloud, but actively evolves on its own.
Exactly.
It's the equivalent of that static skyscraper we talked about earlier, looking at the heavy foot traffic on the street below and suddenly reorganizing its own steel beams to construct a new set of doors exactly where the people need them.
The structure is alive.
It really is. On that note, we're going to wrap up. Thank you for joining us on this deep dive into the blueprint of modern enterprise architecture. We hope you take these concepts, the VIP wristbands, the production parity, and the wild vision of autonomous, evolving AI into your next big meeting or your own personal tech exploration. Until next time.